And here's a second example, and feel free to stop the video and solve the problem on your own. You'll get a lot of benefit that way. We have a step-up transformer, which we're going to use to create a high voltage for a television set in the old cathode ray tube style, which needs high voltage. The output voltage needs to be 50,000 volts RMS, and the input voltage is going to just be the lowly 120 volts. So three questions for you. One is, what is the turns ratio, the primary to secondary, that will give us this step-up voltage? Two, if the output power is 80 watts RMS, what would the output current need to be? And three, finally, what is the input current? So the clever ones amongst you would probably already know that you could figure out the answer to this last one without the previous two steps, but I'd like to know what the answers to all of them are. So to figure out the turns ratio needed to step up 120 volts to 50,000 volts, we just have to divide 50,000 by 120, and those of you who are quick with your calculators will find that that is 417. So we need a ratio of primary to secondary turns of 1 to 417. Now we have the turns ratio. For the output current, we know that we have 50,000 volts RMS, and we're trying to generate 80 watts RMS. So what current do we need to produce that? Well, we can just divide, knowing that the power is the voltage times the current, we just have to divide the power by the voltage, and again, those of you quick with the calculators would come up with the solution that we need an output current of 1.6 milliamps. That's 1.6 times 10 to the minus third amps. Finally, what's the input current? Well, we could use the turns ratio of 417 multiplied by the output current, since this is a step-up transformer, of 1.6 milliamps, and get a solution of 0.667 amps, or 667 milliamps. Another way to do that is to just, the clever ones amongst you will have determined that you could just have looked at the input voltage, knowing what power needs to be produced, 80 watts, divide by 120 volts, and come up with, again, 0.67 amps. So again, either solution will lead you to the right answer. So that's the answer. Oh, by the way, transformers are not always totally efficient. Sometimes they have losses for reasons that we'll go into actually in just a moment. But let's say that you have a transformer that's 70% efficient. That means that 70% of the input power gets delivered as output power, and the other 30% gets dissipated, either heating up the transformer or being sent off as electromagnetic waves. But the way to deal with that is just to deal with it in the same way that you deal with efficiency for work or in thermodynamic processes. So I think you should have no trouble dealing with that. This is the last class, the last lecture on transformers and power lines. And so from power lines, hope you didn't mind the transition there. Power lines, so be able to describe ideal transformers. We did that last time. And basically it's how many coils you have on a transformer. If you go from a low number of coils to a high number of coils, you're going to get more voltage out. If you go from a higher number to a lower number, you're going to get less voltage out, but you'll get more current. So that's how transformers work. And we use that, and it's basically the turns ratio the number of turns that you have on the secondary and the number of turns you have on the primary that determines how much, well, what the voltage ratio coming out is. And that's useful in transmission lines. But, well, we'll talk about where you get power losses and basically how transmission lines, power generation and transmission works. And be able to solve some problems and why it might be a problem. And what risks are involved if you live or work near high power lines, high voltage power lines. And electrical power distribution could be short distances, hundreds of meters, up to thousands of meters that you're using to transmit power. In our country, most of this is alternating current, but there are countries that actually use DC transmission. It's a little more difficult that way, actually. Typically, power distribution is the voltage for these. If you're going for long distances, you're in the hundreds of kilovolts. If you're sort of in the regional area, you're talking about tens of kilovolts. And then if you're talking residential, maybe a couple hundred volts. And if you're using transformers, if you're using alternating current, this is really easy to do because you have transformers that just have different numbers of coils, and you can change the voltages between these very easily. From 100 kilovolts to 10 kilovolts, that's a 10 to 1 ratio, or basically 200 volts up to that. It's basically just the number of turns ratios. And this is a typical transmission power line that you're generating here, maybe on the order of kilovolts, something like that. You bump it up to high long distance transmission of a couple hundred kilovolts. And then where you're going to break it down, step down to on the order of, let's say, 10 kilovolts, and then you use that transformers on the poles, you'll break it down to, let's say, 220 when you go actually into people's houses. And the fact that you're using alternating current and transformers makes it very easy to do. Very easy to do. And so why do people want to do high voltage transmission? Well, it's because it minimizes losses.